Good day, everyone. I am Miss Gian May Morgado, and in this lecture video, I will be discussing with you heat, effects of heat, and modes of heat transfer. But before I continue, I would like to request everyone who's watching this video to prepare the following materials: your notebook, your ballpen, and your calculator. For this lecture video shall include both conceptual discussions and problem-solving activities. So I hope you actively listen to the discussion and actively take down notes. And if you're ready, without further ado, let us begin with the lesson. Here are the following objectives of this lesson. Explain the connection between the zeroth law of thermodynamics, temperature, thermal equilibrium, and temperature scales. We also have to convert temperatures and temperature difference in the following scales: Fahrenheit, Celsius, and Kelvin. And lastly, we have to solve problems involving temperature, heat capacity, heat transfer, and thermal equilibrium. So in order to understand the concept of heat and all its workings, we must begin with a term that's basic and most familiar to all of us, and that is temperature. Before we define temperature, let me ask you first this question. Maybe you're a coffee lover like me. Do you also enjoy a warm cup of coffee on cold days? And if you do, what do you do to know how hot or cold a beverage is? Do you just compare it with the temperature of your hand? And if it feels warmer or hotter, you say that its temperature is high? And is that enough to actually say that the temperature of the object is high? Now, that's just one of the problems that we find difficult to understand in physics, but I hope we understand that question further in this video. Our common connotation to the term temperature is that it is the degree of hotness or coldness of a material. But that definition is quite vague because it must mean that it is in reference to another object. To describe temperature, it is actually rooted in the molecular movements of the particles because temperature is the average kinetic energy of the molecules of a material. Now, if you will recall the term kinetic energy from our previous discussions, kinetic energy refers to the energy possessed by objects in motion. So we all know that particles in a material could either vibrate or move freely. In this case, the motion of those particles define or tells us the temperature of the object. And it has been found that the greater the kinetic energy of the molecules, which means that the greater is the motion or the more rapid is the motion of the particles, considering also the collision, the greater is the temperature, as shown in this figure. Why? Because as the particles move or vibrate, they collide with other particles, and collision produces heat. That in turn creates the temperature that we can feel. Okay, if you will consider a box, okay, containing particles, and these particles move rapidly, we can say that the particles in the object rather, has a high kinetic energy, and in turn, the material has a high temperature. Okay? Now we will explore this relationship further through a simulation known as the PhET simulation, the properties of gases. We have seen from the simulation that when heat is added into a material or a system, the liquid in the thermometer rises. Now that rising event in the thermometer is an indication that the material or the liquid in the material reacts to the added heat because most materials have a property that varies with the degree of hotness and coldness of a material. So a thermometer is actually just an object that reacts to the temperature or heat rather that is added into a system. Aside from that, that expansion of the liquid in the thermometer is not just the only property that is affected by the addition of heat. We also have length. The length of materials normally increases when heat is added, and as well as the pressure, as you have seen in the simulation. And also, electrical resistance of the material is affected when heat is added. We'll discuss electrical resistance further in our next lessons. So how does a thermometer actually works? A thermometer actually measures its own temperature by thermal equilibrium. Yes, it means that when you're reading the temperature through a thermometer, what you're reading is actually the temperature of the liquid in the thermometer. What happens is that when two bodies are in contact, one of the objects transfer heat to the other. What do we mean by that? If you have a liquid, say that has a certain temperature, if you submerge a thermometer in that liquid, the liquid in the thermometer will absorb some of the heat of the liquid, and that absorbed heat will cause the particles in the thermometer to move rapidly. And so once those particles in the thermometer move rapidly, it suggests that the kinetic energy of those particles, average kinetic energy of those particles, will increase, and in turn will increase the temperature. And that temperature is the temperature reading that you can see in the thermometer. What happened there is actually thermal equilibrium. It is the state in which the interaction between the objects cause no further change in the system. That's why when you submerge a thermometer into a liquid, or place it in or put it in contact with another object that has a certain temperature, you don't immediately get the reading. You have to wait for a few minutes until the reading stabilizes, because you are waiting for the thermal equilibrium. What To explain it further, observe the GIF in this presentation. You have object A and object B, two objects with different masses and with different temperature. Initially, object A has a low temperature and object B has a high temperature. Once you put them in contact, you'll notice that object B loses its temperature, while object A rather increases its temperature. What happens here actually is that the hotter object transfers some of its heat to the other material, object A, and object A, being the one with the smaller or lower temperature, absorbs the heat, and in turn its temperature increases. So as two bodies interact, one body transfers heat to the other, and they will eventually reach a steady value known as the thermal equilibrium condition. Not all materials, when placed together, can transfer heat. There are also some materials that prohibit the transfer of heat, known as insulators. An insulator is a material that is a poor conductor of heat or electricity. It does not necessarily mean that insulators will not allow the flow of heat or totally not allow the flow of heat, but rather they just slow down the transfer of heat. So it takes a while before the heat is fully transferred to the other object. Some of the examples are glass, rubber, plastics, and cloth. Now, in contrast, we also have materials that are good conductors of heat. They are the conductors. These are materials that allow energy in the form of heat to be transferred within the material without any movement of the material itself. So there is no necessary movement in matter. There is just transfer of energy due to the collision of the particles in the material. So some materials have particles that can easily transfer the energy or heat through collisions of particles. Imagine the particles of, let's say, metals like copper, brass, steel, gold. These metals have a certain structure in their molecular um, uh, structure that allows them the molecules to collide faster and move or transfer the energy faster throughout the material. Moving forward, now that we have defined the terms temperature and thermal equilibrium, let us discuss the important and basic law of thermodynamics known as the zeroth law of thermodynamics. To understand zeroth law, let's use this figure. In this figure, we have three systems, system A, B, and C. We can also see in this figure that system A and B are separated by an insulator, and on the other hand, system C is separated from system A and B with the conductors. Now, here are my questions. Is system A and C in thermal equilibrium? Do you think they have the same temperature? The answer is yes. Yes, because system C is in contact, or not necessarily in contact, but there is a conductor between them, separating them, allowing heat to still be transferred to each from C to A. And so there is a chance that A and C will be in thermal equilibrium. Another question, is system B and C in thermal equilibrium with each other? Answer, yes. It is There is still a chance that they would still be in thermal equilibrium because C is also in contact or can transfer heat through system B through a conductor. But the main question is, are systems A and B in thermal equilibrium with each other? The answer is still a yes, because since system A and system B are both in thermal equilibrium with system C, we can assume that A has the same temperature with system B. And so they have, or they are in thermal equilibrium. To prove that, we can actually change the setup. If we replace the insulator that was initially separating system A and B with the conductor and place an insulator between systems A and C and systems B and C, okay, we will notice that the systems A and B will not transfer heat to each other, which means that these objects or systems are already in thermal equilibrium with each other. So the zeroth law, if we'll state it in words, is that the zeroth law of thermodynamics states that if two bodies are each in thermal equilibrium with the third body, they are also in equilibrium with each other. By figure, this is what happened a while ago. Figures or systems A and B initially had different temperatures with respect to each other and with respect to C. But since they are both in contact with system C, they shared or transferred or gained heat rather from system C, allowing them to have the same temperature with system C. Now, if we will separate system C from the setup, we'll notice that B and A, or systems B and A, already have the same temperature. As defined a while ago, temperature is not a qualitative property but rather a quantitative property. So to quantify or measure the hotness or coldness of a material, we have to use a temperature scale. Now we have three common temperature scales. We have the Celsius temperature scale, known before as centigrade, Fahrenheit temperature scale, and Kelvin temperature scale. Now these three temperature scales have different freezing and boiling points. For Celsius, the one that we are familiar with, we have 0 degrees as the freezing point and 100 degrees Celsius as the boiling point. Fahrenheit, on the other hand, has a 32 degrees Fahrenheit freezing point and 212 degrees Fahrenheit boiling point. For Kelvin, it's a higher number, 273 Kelvin and 373.15 Kelvin. 373.15 Kelvin. 373.15 Kelvin. Okay? Now, the SI unit, however, used in temperature or describing temperature is Kelvin. This is derived from Lord Kelvin. And it is not correct to say degrees Kelvin. So never say degrees Kelvin when describing temperature using the Kelvin temperature scale. Degree is not used with the Kelvin scale. To compare the three temperature scales, we can see in this figure that both Celsius degree and Fahrenheit have the same difference in temperature for the boiling and freezing points. On the other hand, degree Fahrenheit has a much greater difference in temperature between its boiling and freezing point. It's 180 degrees Fahrenheit. This suggests that we cannot easily convert the magnitude or value of a Celsius temperature to Fahrenheit. There is a specific formula to it. On the other hand, converting Celsius temperature to Kelvin temperature is much easier because they have the same difference. Now, aside from that, we can see in this figure that the scale, the 0 Kelvin at the bottom represents the absolute temperature scale. And it is at 0 point, where the temperature is 0 Kelvin and the equivalent value in degrees Celsius is negative 273.15 degrees Celsius. Here, in this particular temperature, the pressure is said to be 0, and so it is called the absolute zero. What do we mean by absolute zero? It is the time where the system has its minimum possible total energy, or the particles inside the system are moving at its minimum value, the lowest possible value or motion, the slowest motion that the object could actually, or particles in the object could actually move. These are the equations that we can use if we want to convert temperature scales. For example, we want to convert Celsius to Fahrenheit. All we have to do is to use the formula T sub F, or temperature in Fahrenheit, is equal to 9/5 times T sub C, the temperature in Celsius, plus 32. Now, we do not recommend that you actually memorize them, but we want you to understand the structure of the formula. Consider the first formula. The given fraction here is 9/5. This is actually from the ratio of temperature in Celsius. The difference between the freezing and boiling point from the previous slide is that for the degrees Fahrenheit is 100 degrees Fahrenheit. On the other hand, for Celsius, it's only 100 degrees Celsius. If we will lowest term, get its lowest value, that's just 9:5. So to convert the given temperature, degrees Celsius, into Fahrenheit, you just multiply 9/5. And notice that the numerator has a higher value because we are expecting that the current degree Celsius value will increase or has a higher degrees Fahrenheit equivalent. Plus we add 32. Next, we if we will convert Fahrenheit to Celsius, we'll use the same ratio, but 5/9 this time, times the quantity T sub F, or given degrees Fahrenheit, minus 32 degrees. So minus because the unit that we're trying to convert into is a smaller temperature scale, thus we have to subtract, plus the numerator here, as you can see, is lower because we want to get again a lower value. Celsius to Kelvin, on the other hand, is very simple. The equivalent Kelvin temperature is just the sum of the given temperature scale in Celsius plus 273.15. From the previous slide a while ago, you've seen that 0 degrees Celsius is equivalent to 273.15 Kelvin. So whatever given value of Celsius temperature, you just have to always add 273.15 to get its equivalent Kelvin. Let's try using the formulas a while ago in a practice problem. You place a small piece of ice in your mouth. Eventually, the water all converts from ice at T sub 1 is equal to 32 degrees Fahrenheit to body temperature. Let's take note of the body temperature. T sub 2 is equal to 98.60 degrees Fahrenheit. Express these temperatures in both Celsius degree and kelvins and find the difference in temperature, or delta T is equal to T sub 2 minus T sub 1 in both cases.